Next, let's see how to get the confusion matrix for our data to take a look at the sensitivity and specificity of our model. So we've got our same data, mortgage data, event of interest 1, approved, it's our response variable, credit score, our continuous variable, main effects model, no selection. Under options, we've got all plots, but now under statistics, I want you to pull that down and select the classification table. So now we can go ahead and run. The output from this is actually a little different than in the previous program that I've used, and so we get kind of an ugly looking classification table here. Here we go, here's this whole thing. What the heck is going on here? Well, what's happening is SAS Studio is showing you all of the probability levels, all of the possible cutoffs in increments of 2%. So we've got 51 lines to this table, 51 rows. I want you guys to concentrate on the very middle row here. Okay, so that's the cutoff of 0.5. That's the first cutoff that I use to make the confusion matrix and the sensitivity and specificity output on Blackboard. So you should recognize those numbers. 245 is the number of people who were predicted to be approved and were actually approved. 565 is the number of people who were predicted to be rejected and were actually rejected. And then we've got 73 and 117 over here, which are, let me show you the top of the table, incorrect event and incorrect non-event. I don't know about you, but I struggle to remember what exactly that means. And so there's a couple of ways that you can help to remember what is happening here. The first clue is the top line in this table here. So the top line in this table uses a probability level of 0. So what does that mean? Anytime somebody's predicted chance of being approved is 0 or greater, we're going to predict that they will be approved. So this is obviously a silly model, but what this means is that we're going to predict everyone is approved. So that tells us then that this number is the number of people who are predicted to be approved incorrectly. So that's your way of reading it. Read event incorrect. Instead of incorrect then event, read event then incorrect. 638 people were predicted to have the event be approved, but that was incorrect. And so then if we scroll down, this means 73 people in our model were predicted to be approved, but were actually rejected. So that would be the bottom left cell in our confusion matrix. The other way that you can use to remember this is to think about how many total people are approved. And so in these data, 362 total people were approved. So now if we go down here, 245 people were approved and were predicted to be approved and were actually approved. But we need to make that up to 362 people who were actually approved, so we would need to add these 117 here. So these must be people who were actually approved but were predicted to be rejected. So 117 people were predicted to be rejected but were actually approved. Okay, so that's the first confusion matrix in our Blackboard text. But there was another one, right? The confusion matrix cutoff equals 0.25. All right, where's the 0.25 line on here? Well, obviously that was a trick question. There isn't one. So how did I get that data? I'm going to show you something here that I haven't shown you guys before, which is that you can actually change the code that SAS is using to run its model. So SAS is in addition to the company that produces the software, SAS is also what the programming language that they've created is known as. And so every time we've been running code, every time we've been running models, doing anything with data in SAS Studio, it's been generating this code in the background that in theory we could have edited. And so if we go to edit here, it creates a new program for us. The particular thing that we need to alter is an option for this C table. So C table is the classification table that we just created. And if we type in pprob, this is going to allow us to select a particular probability level. So if I select pprob equals 0.25 and hit run on this custom code that I've created, then we're just going to get a single line in that table now for the cutoff value of 0.25. So here we are, that's that new classification table that I created, or new confusion matrix that I created in the on Blackboard. Here are the numbers that I used to create it. Over to the right on this table, you've got the sensitivity and specificity of your model. If we go back to the output from this model, what you'll be seeing is that the sensitivity is very high when our cutoff value is low. Our specificity is low when our cutoff value is low. Let's think about why that is. Well, when we have this cutoff value of 0, we're just predicting that everybody's going to be approved. And so if we think about what sensitivity is given that we were approved, how many people were correctly approved? Well, 100% of those were correctly approved. And so our sensitivity in our model is 0. What about specificity? Well, this is for the people who were rejected, how many did we correctly predict would be rejected? And, well, none of them. We got all of them wrong. So our specificity is 0. Now, as we increase this cutoff value, the sensitivity is going to decrease because we're going to start getting some of those actually approved people wrong, but our specificity is going to improve. We're going to start getting some of those actually rejected people correct. And as we scroll down through those probabilities, our sensitivity is going to be increasing, our specificity is going to be decreasing. We can actually get a picture of this all at once. That's this ROC curve, where we plot the combinations of sensitivity and specificity. Actually, strictly it's 1 minus the specificity. And then particular cutoff values will give us a particular point on this ROC curve, the receiver operating characteristic curve. And so I labeled the two that I did on Blackboard on that ROC curve that I showed for you guys in Blackboard.